Yeah, okay, okay. So good evening, everyone. So this is our first tutorial session for the NPTEL course on the foundations of wavelets and multi-rate digital signal processing. And as you already know, I'm G.R. Krishna, a PhD student at the Department of Aerospace Engineering, Indian Institute of Science. So I'll just be a TA, like we would be uh, mainly discussing whatever has been taught in the course and also try to do some extra things as well. Right? So yeah, before that, could you please introduce yourselves? So let's start with Jaswant. Jaswant, hello. Are you there? Can you please unmute and just give a short description of yours? Like, what are your, uh, what is your background in terms of academics?
Sorry for the disturbance due to some
Sure,
signal.
sure,
I'm speaking now. It's okay, sir. Let's go ahead.
sure, sure, sure. Yeah. So could you please introduce yourself? Like, uh, what, uh, what branch of engineering, if you are, then which branch of engineering?
Sir, myself, Jashwant. I am from Satyabama University, ECE.
Huh. Okay, okay. So you're a bachelor student, huh? Or
It's a bachelor student.
I see, I see. Okay,
I'm
nice
a
to know.
first year student. I'm a first year student.
Okay, you're a first year student. I see. So it's like, yeah. So for me also, like I'm not very much into. I'm from aerospace background. My specialization is structures, but I have some time back did some just some I would say study on wavelet analysis as part of some other course. So that's the reason I don't have pretty much background in this area. Yeah. So next there is this B Sainia. If I hope I'm spelling it right.
Yes, sir, it is shiny. Yes, sir.
Okay. Okay. So could you please introduce yourself?
Yes, sir. Okay, I'm shiny. So I'm going to pursue my PhD. I have just registered now.
I
So
see.
I'm also from the EC department, sir. It is related to my project is related to wavelets. So
Okay.
yes,
Okay.
so that's
Okay.
why I joined this. Yes, sir.
Okay. So you're in uh, like if I may just ask, so you are doing your masters, am I right, or bachelor's?
Yes,
Like
I'm going to do my research, sir. PhD.
okay,
I have
right now.
finished my masters. Yes,
Okay, you have finished master. I see. I see.
yes,
That's good to know. Yeah.
yes, sir.
So I like as I have already mentioned, like I am not I'm not an expert, so to speak. I don't have say formal academic background in wavelet analysis, but yeah,
Okay.
I have just did some study as part of some course that I did. So since wavelet has applicabilities in multiple areas, right?
Yes, sir.
Even despite inspire, I mean, not only in electronics and I mean, electronics and communication engineering, but also it has applications in areas like fluid mechanics, signal processing. I mean, fluid mechanics, wherever you have signals.
Yes,
So
sir.
essentially, yeah. So in a sense, wavelets are much like Fourier transform. So they all belong to the branch of applied maths, but they are used for various purposes according to the needs of the situation. Right?
Yes, sir.
So okay, so we'll just like so what are your expectations from the course? Like if you have certain expectations, then we can work it out together as well. Like since this is more like an informal meeting, uh, although say officially facilitated by NPTEL, but it's more of an informal meeting. So if you have certain requirements, certain say expectations from this tutorial session, then we can even pursue things which are not covered in the NPTEL lectures.
Okay, sir. Actually, I'm totally new to this. Just now I have registered.
I
So
see. I see. I see.
yes, it is based on wavelets only. We are going to denoise the signal.
Okay.
So
Okay. Okay.
I just need the basics of
I
yes.
see. Okay. Okay. Okay, so let me just start with a brief description. Although in the first week of this course there was nothing much because as I even went through myself the videos and all, so I didn't find there is much to be discussed. But inspired, despite that, I will try to talk about certain ideas which were not, which are say beyond what was discussed in the course, right? So I'll just first of all we'll start with what do we mean by introduction. I mean, what are wavelets, right? So we'll start with an introduction to wavelets. So before that, I had wanted to discuss about something like what do we expect from this course, right? From this discussion meetings, so to speak, right? Or the tutorial sessions. So first of all, we will revise whatever is covered in the in the course lectures. Revise whatever has been covered in the course, been covered the official course lectures. Right? And so official lectures as part of the in the that has been covered in the week. And secondly, we would go a step ahead. We will do, of course, since the way it is scheduled, it seems that the lectures will come say faster than the assignments. So it seems that I cannot tentatively cannot solve assignment questions, but we will try to do something, just some altered version of the assignment problems, some altered versions, or maybe some assignment like problems. Right? And thirdly, we would also be doing some programming. So we will not leave that, since ideas like wavelet analysis are not just mere mathematical abstractions, rather they have some practical implications as well, right? So we'll also do some programming. So Shiny, which have you by so far, I mean, which packages have you thought of using in your project? Like which softwares?
Like MATLAB, sir.
I see. Okay, so
So,
okay, so you are specifically will be doing using MATLAB, right?
yes, sir.
Okay, so what I'll try is to do is initially I had planned to do it using one open source package called Wavelets. So it's a Python-based package.
Okay.
But of course, we can supplement it using some MATLAB codes as well.
Okay, sir. Okay.
So the reason being that Python scripts run much faster than MATLAB, right? And it's also lightweight, so you can do heavy computations using less resources.
Yes, sir.
But again, we'll see how does MATLAB fit into that. We'll also try to do in say do some problems in Pi wavelets and also do some in MATLAB. So I think that will be like learning from both these software environments, right?
Yes,
So this
sir.
is essentially what we are planning to do. So we'll also try, of course, not only try, we will actually do some say signal analysis using wavelets. So that will do as we learn maybe from the, if possible, from the next tutorial. I mean, next tutorial session itself, we will just try to even dive into that areas. So that is the so to speak, a very rudimentary level or maybe some very tentative plan, but we will stick around the points that we have mentioned here. Right? So today we'll go through the overall nitties gritties. Maybe we can even go further than what was taught in the week one, but I think that is the whole purpose of these tutorial sessions. So essentially, little bit of history that these wavelets as a concept was introduced by Ahar in his thesis in 1909. So he was a mathematician. So that is where he introduced this concept of wavelets. And by the very name, wavelets is like if you just break into two, right? It's something like small waves or like children of waves or something like you can just call it waves, small waves or like wave-like entities. Then further, so there is this the introduction part, and in 1930s there was a physicist called Paul Levy. So he was a physicist. He investigated Brownian motion, and that is a type of random signal using Haar basis function. Then there was in 1980. Of course, these are just some scattered pieces, but in 1980 there were these two persons called Grossman and Morlett, and so Grossman was a physicist and Morlett was an engineer. So they defined wavelet in the context of quantum physics. Right? Then after some time, in later in the 1990s, so there was a very famous Yves Mayer. That's how I'm pronouncing it. So he was an applied mathematician. He was an applied mathematician. So he played a very pivotal role in the further development of wavelets during 1990s. Right? And it's very remarkable that he was awarded the Abel Prize for this. So he was awarded the Abel Prize, which is considered around the world to be the biggest prize, so to speak, or biggest prize in the domain of mathematics, right? So although his work was during 1990s, but eventually he was rewarded in 2017 for his work, and he also had a lot of he did a lot of research in the area of harmonic analysis, right? So all those areas involve doing a lot of functional analysis as well as uh, yeah. So it's mainly functional analysis. Then through that you form many other aspects. You also cover many aspects such as say Fourier analysis. Then of course that's what we are dealing with today, which is wavelet analysis, right? So That's how it started, right? And so first of all, we want to understand why why wavelet transform. Now the question comes, right? So far so good. So we will ask a question: why wavelet analysis or why wavelet transform? And actually, that is the most interesting aspect of wavelet transform. That although by this time Fourier transform was already very much popular in signal analysis, then what was the need of introducing a new type of transform? So that was the very it was a very say of course an obvious question, right? So there are uh, certain issues here. Well, I mean, there are certain problems with Fourier transform, and of course, I'll just share you a figure later, but let me just draw it now. And I think that clears a lot of the, so to speak, the confusion or maybe even the curiosity about having a new type of transform, right? So say this is frequency axis and this is the time axis. And let it be for both sides, right? Frequency and time. And you know, for any signal, right? So which we pick any signal, say any signal, this is some arbitrary signal, right? So there's some signal, some time signal. It can even be spatial signal, but for now, let's consider it to be time signal, right? So say you have a such signal, right? Any arbitrary signal, and you want to say you first find the Fourier transform. So I don't know how many of you will be familiar to Fourier transform. So let's go a step backwards. And let me also introduce what is a Fourier transform. I think that is a better way to uh, move in this direction, right? So let's start. What do we mean by Fourier analysis? Generally speaking, what does Fourier analysis do? So, of course, Fourier analysis is a very broad term. In that is more like a mathematical language. So the applied part, say the applied Fourier analysis is what we would call as the Fourier transform. And Fourier transform holds for a generic signal, any general arbitrary signal. You can try to understand or try to determine which all components form it, right? That using Fourier analysis, Fourier transform, that is the operational aspect. So this is like the operational version. So first of all, the question comes like we would go a back again a step, we would take a step backwards. So the question is, what do you mean by a signal? What is a signal, right? So there is a very I like I would present a definition which I had to learn somewhere that signal is any measurable quantity, right? Any measurable quantity which varies with time. And of course, this varies as a very I mean as expansive meaning as possible. So it can even be you would ask, okay, the thing is, okay, if it needs to vary, then can DC signal be also called a signal because it does not vary? But yeah, it's like something, to be more precise, anything which is dependent on time, or maybe more formally, something which can be say parametrized in time. That is, I think, a better word. So as time changes, the value of that signal exists, right? So that is what we mean by a signal. So anything. So it can be, say you have uh, say for example, you have a battery, right, or a cell, so to speak. Thus, you have a cell. Of course, there's positive and negative. Then you are just applying a voltmeter, and there's just trying to understand. There's some voltmeter, right? and you are measuring the so the voltage across the ends of this across the terminals of this cell. So there is a cell here. Then we would ideally say that, okay, since it's a DC cell, because let's say we are taking some DC cell, right? Some direct current cell. You'd say, okay, but the thing is, it should be constant, right? But the thing is, because of the chemical reactions, the voltage is also not going to be constant, right? If you plot the voltage along time measured by the voltmeter, then of course, if it is rated to be 5 volt, then say we just mark this line as 5 volt. So this is the voltage axis. It will always keep on oscillating about this, like varying, maybe either about, but around the value of 5 volt. Right? So even this is a signal, if you call it, because there is some measurable quantity. So measurable quantity happens to a voltage here, or the voltage signal, and it varies with time. Right. So that is how you define broadly. So this was just one example. There are many such examples. For example, you have a you fix say a scale that we usually sometimes you may have seen that steel scale, right? So you have a steel scale of 30 centimeter. You fix in some portion of the wall and then just vibrate it, like apply a just pluck it at the end. So what it will do is it will move up and down about this horizontal axis, and it will be creating some displacement, right? So the displacement here, like how much it is moving away from this position, like up or down. So this is like displacement, let's call it y. So if it is upside, then it is positive direction, and if it is downside, then it is negative direction. And if you say plot it, then it will also be some, of course, like let me just make some arbitrary, but it has to satisfy certain physical relations. Say this, you have y as a function of time. So even this is a signal, right? Since you have a measurable quantity, which happens to be displacement. So broadly, that is how we define a signal, right? I hope that is clear. Now, once you are clear with this, then only we should we can move forward from here. So say given a signal, just take the displacement signal from here, right? Just the one that we drew about some axis, some y is this is y positive, and there's of course negative and positive, and there's zero axis. So you have varies with time. Now the idea of doing transform. So why do transform? Why do we want to determine the transform of a signal? Now, of course, I may not be very much well versed, but the things that come into my mind are number one, for the sake of storage at first. Or maybe this would not be as important. Of course, it is also a part, but first of all, we want to understand the underlying properties. So underlying properties are things such as frequency and its corresponding, and also the amplitude. So these are some underlying properties of a signal that we would want to understand for a signal, right? Knowing frequency helps in many ways because, like for example, say when you are sampling data from some device, that's also when you want to know the frequency at what should be my sampling rate so that I can the best sampling rate so that I can sample and be able to capture the say the variations within a signal, right? So that is where we want to understand about frequency. And in a more broader way, say if you want to talk about in structural mechanics or say structural dynamics, which has happens to be my background. So understanding frequency of a signal helps us to understand the natural frequency of a structure. Right? So if through the measured signal, we want to either I mean we want to understand the natural frequency of a signal, or we can also learn about what signals, what components in the signals is not desirable for the stability or for the real, I mean, so to speak, the reliability of a structure. I know I'm just going tangent to our discussion, but that's what I just want to let you know. And then, of course, the second part also comes to be about compression, about data storage. You cannot say store the entire data, because it makes no sense to say stores GBs and TBs, even petabytes of data without making any sense. We want to make some sense of the signal that we have in our hands. So that's the reason we do Fourier transform, any such transformation through which we can capture the most important parts of a signal, which are like frequency and amplitude, and then take it, and we can just uh, and then throw away the rest. Now you will see, okay, what are the advantages of that? So, for example, when you in a telephone in a telecommunication network as well, right? We do not say, if I mean just even right now, whatever I'm speaking, you may not be hearing the entirety of what I'm speaking, like the entirety of the entire say the sound waves that I'm producing, right? The reason is because in a telecommunication network, the first of all, what I will be speaking, so even this is a signal. It just happens to be a sound signal, right? So it's more like a pressure signal. Then there will be some device which will convert it into electrical signals, and even during this conversion, there is a lot of information which are lost, right? And then and of course, but it will still keep the important parts of the signal, and then it will transmit it, right? So during that time, it will be some sort of a modulation. I hope I'm using the correct words. So it will be the signal will be modulated, and only the important parts will be kept. And then this will be, say, sent through the network, and then there will be some sort of a demodulation, like, or maybe some sort of a I think decoding, I think that's how we can call it. So in this process, when you move from say modulation and all, so I'll be speaking something. There will be some converter which will which will transform the signal, and it will only send the it will send some of the significant parts of the signal through the network, and then it will arrive on the other end. So this is like it will be first I mean, what can we say? Something like it will be deconstructed, like the signal will be broken down, and then it will be reconstructed at your end right now, right? It will be reconstructed. So even during this process, there is some sort of a what we call the analysis involved, or the transformation involved, right? So that is what the generically we are talking about. Now, if let's go and ask ourselves, uh, what are the components of a signal, right? So you have any signal, right? What are the components of a signal? Say I'm taking a signal with constant amplitude. So the upper level and the lowermost level happens to be equal for every, I mean, at every instance, right? So say this is like the A, and this is of course T, right? So A is called as the amplitude of the signal. And then what you have is the signal is repeating after some time. Say from, if you look at this portion and in this portion, after that, what you see is the signal happens to be repeating, right? So it means that this particular segment is what we call as it's the time period of the signal. So this call as referred as T, right? And there is one more term called phase, which happens to be how much shifted. is the signal from some reference point. I will not be talking because it's not. I mean, of course, it's also a part of signal, but by shifting, you can anyway convert your phase to zero. Like it's just some signal shifting where you can make this phase to be zero. So it depends on your reference point, right? From some reference point, right? So right now we are focusing on amplitude and time period. Now the frequency is what we are talking about. Is called as, oftentimes I'm sure some certain books prefer nu, but let's call it f. Certain books also prefer f. It's denoted using f. So frequency is 1 by t. So it's like what is it's like ideally it's just the uh, reciprocal of the time period, right? So time period usually will be SI unit is seconds, and frequency, it is of course per second or hertz, right? And then there is one more widely used notion of frequency, that is what we call as the angular frequency. So angular frequency is omega, denoted by omega, and this is given by 2 pi f, right? So sometimes people just use frequency instead of angular frequency. Like, even we just call omega as frequency. However, to be more accurate, like frequency is just the reciprocal of time period, and omega or the angular frequency happens to be 2 pi into f, right? Okay, fine. So this was since this signal has just one frequency, right? So this signal has a single frequency. Right? So such signals we call as monochromatic signal. So since it has just of course, chrome we also always associated with light, but in this case, monochromatic in a sense means it is a signal with a single frequency. So which means that this is a base signal, right? So this signal happens to be a base signal. So we can say represent this signal to be, say, let's call it x of t is equal to a, of course, a is the amplitude, sine omega t. That is how we usually write, right? And of course, this can be written as a sine in variety of ways, 2 pi f t. This is also the same as sine 2 pi by omega, 2 pi by capital T into small t. Various ways of writing it, right? So which means that here, this is a base signal because it has just one frequency. So we can also call this signal as a fundamental signal, right? Or a fundamental component of a signal. Or just a fundamental signal, because you cannot go lower than this, right? So to express the signal, you actually have to express it as it is, a sine omega t. Now let's move a step forward. Say you have a signal, let's call it y of t. Right? I don't know whether I'll be making the right drawing, but say I'm uh, some sort of a, okay, let me try again. This please do not take it to be it's just it's just some sort of a schematic, right? So this is some signal, right? Y of t. And you have constructed this by, say, a1 sine omega 1 t plus a2 sine omega 2 t. Fine. Let's say this is a schematic. Please do not consider it to be the actual representation of the signal, right? See, this is a signal which is constructed using two components, right? So from here, when you look at the signal, of course, uh, we would we would want to understand, say, from here, to here is fine. So this is like a forward problem, so to speak, right? It's quite forward. You have the signal, you plot it. At this moment, this is non, and you have just calculated this. What if it's the either it's is the other direction? What if this is non? What if when you have say you are given this signal and you want to express it in terms of you want to represent it mathematically of the same signal of the non-signal? Then of course you cannot just look at the signal and get, I mean, just try to cook up some component description, right? You would want to analyze the signal, right? So when you want to representation of, I would say not the non, but say representations of some given signal. So here is where the concept of transform. So here is where we need transform. We need analysis or maybe some transformation method to get this, to get the representation. So that is the concept of why do we need some transform, right? Or say Fourier wavelet or whatever transforms like there, you can just construct your own transform, provided it has it fulfills certain requirements or properties, right? So there is where we have to, or we need some transformation approach where we can get the essentially are able to construct the signal mathematically or get the representative of the signal mathematically, right? So of course you would ask, okay, but what is the solution now? Right? So in a sense, you have given some signal y of t, right? And the goal is find its representation. Right? Then one such, of course, a very famous method is, of course, what you call as the Fourier analysis. And one which you may have studied during in some engineering or engineering-like courses is what we in the you may have learned about, like Fourier series, right? So I'm just calling it Fourier series because Fourier series, what you learned in classrooms and all, is just one special type of Fourier analysis. Fourier analysis is quite vast, not just sines and cosines, right? So one such thing which comes to our rescue is Fourier series. So what you do in Fourier series is you want to express any signal. Say to distinguish between this previous signal, let me call it y, or maybe just say x of t, just to distinguish between so that because we'll be using that signal to get some important ideas about the signal, right? So x of t can be broken down into some a naught plus summation of, or maybe let's start it first before I use the summation notation, a1 sine omega 1t plus a2, or maybe plus b1. I think in generally we see cosine first. So okay, b1 sine omega 1t plus a2 cosine omega 2 omega 2t plus b2 sine omega 2t till infinity, right? So this happens to be series. It's a Fourier series. I mean the well-known Fourier series, right? And then you can have it as, some books also prefer it to divide by 2. So I'll just divide it by 2. And then summation of n is equal to 1 to infinity, and a1 cosine omega an cosine omega nt plus bn sine omega nt. Right. So this is the Fourier series representation. Now you ask, okay, so it's known that xt is like known, and I have mentioned it already. I had mentioned it before. So this xt is known, but this all the constants a naught and also say A1, A2, and all, and then B1 till say B infinity, whatever. And even what we'll have is that even omega n happens to be n of omega naught, right? So omega naught is what we call as the fundamental frequency. Right? And then other n, omega n will just be a multiple of the fundamental frequency. So such series or such series or such signals are what we call as a harmonic series or maybe harmonic signals, right? Where all the signal components happen to be a function of some particular fundamental frequency. So if we have a harmonic frequency, if we have a harmonic signal, or if say if x of t is harmonic, then the representation will be finite. The representation of the signal in Fourier basis or in Fourier using Fourier series is going to be finite. Is finite. Now the question comes, what do we mean by finite here? So what we mean here by finite is that you need not know all the coefficients till infinity, right? Only few of them you can obviously just construct it. I think it's harmonic, or let me say it periodic. I think that is usually more appropriate. If the signal f(xt) is periodic, then this representation will be, I would say, okay, let me just cut this back. So this representation will be uh, uh, okay, so we can represent it, and then all the representations of A0, A1, I mean, all the components will be quite well known, right? And you can, of course, get it by using that, if you know all that mathematical relations that we have, right? So you integrate xt over the given frequency, right? Xt, and then first of all, that it will be just average out to get a naught. You just have to average out over one time interval or one time period, and then divide by t. So this will give a naught. Likewise, and of course, since we are using 2 here, so it will be 2 by t. And for the rest, say you have an is equal to, I hope this is right, and I hope this is right, yeah, because it has been quite some time. So maybe this will not be fully, I'm not fully sure right now, and I'll not be deriving because of this not being a part of our interest right now. Say n omega naught t dt, right? And likewise, bn will also be some factor into xt, and then you have sine n omega naught t dt and integrated over half the sum domain. Fine. Okay, so this we have, right? So what we would do is, now you'll ask, fine. So this was just a very extremely rudimentary or extremely short revision of Fourier series approach. And you'll ask, okay, so given that you have this signal here, right? So we had this signal. I'll just copy and I'll try to paste if it's possible. Okay. Yeah. So this is time. So here is where we'll be using such ideas, right? So this Fourier series ideas. And what we get to know is, we know, and let's see, this is behind this in the black box, that y of t is equal to a1 sine omega 1t plus a2 sine omega 2t. So this just say that it is in the black box. Fine. We only know this. So we say that we only know this. This is hidden in under some black box. And by the look of it, it looks that the signal is periodic. And let me make such that the upper and lower, sorry, that the limits should be okay. So what we see is this signal is repeating. So say we are just looking at the at some, say, where it crosses, and after which the signal starts repeating. So it seems that signal is repeating after this. Right? So after this length, the signal is always going to be repeating. So by visual or by what we call by our investigation, or by our, say, first-hand investigation, what we see is the signal is repeating after t, after time t, right? So which means that this is a periodic signal. That is the first. This is a periodic signal. And you must know that the Fourier series approach can only be used to decompose a periodic signal. That's it. So to use Fourier series approach, the first requirement is that the signal must be periodic. Otherwise, we cannot get the frequencies in terms of the fundamental frequencies, right? So then the approach becomes a very generic thing, what we call as the Fourier transform, where omega need not be multiple of some fundamental frequency. So by inspection, you saw that, okay, this is a periodic signal. So we can use Fourier series approach. Then what we do is, and say A naught is equal to 1 by t, right? And the integral from minus t by 2. And of course, what I had used is 2 by t. So yt dt. And what you see is yt dt integrated over this time interval. Say it happens to be 0. Integral. So it's like the positive area and the negative area happens to be cancels out each other. So this is like 0. Fine. Second thing, let's also determine an. So an will be is equal to, again, I'm not sure, I'm just using this some constant multiplier. Of course, we can easily get it, but let's leave it because it's as of now, right now. And then what you'll have is y of t and then cosine of t. And of course, it was n. And since we are using multiplier, since the signal happens to periodic, it's a multiple of some fundamental frequency. So 2n 2 pi by t into t dt. And this, what we see is, it's also evaluates to 0. Say it just evaluates to 0. Fine. Now, and the answer, I mean, I'll just get let's know why it happens. Then, of course, one more multiplier factor. Then you have t by 2 minus t by 2, and then y of t sine n 2 pi by t d dt. And this happens to be some value. So some value. So this is some non-zero value. But again, what you'll see is non-zero only for some non-zero value. Okay, fine. Now, however, it so happens that for n is equal to 1, b1 is not equal to 0, and n is equal to 2 also, b2 is not equal to 0. For n greater than 2, bn is equal to 0. Okay, so that is what you have understood. Got the, say you are able to get the Fourier sign, the coefficients of the Fourier series. Now what you see is, we can now express yt in terms of all that. So a naught by 2 is 0 by 2, so it is 0. Then all the a's are 0, which means that, of course, there will be no cosine term. And also what we see is that B1 is non-zero, and then it will be multiplying sine uh, 2 pi by t into t. And also B2 is zero. B2 is also not zero. So it was like B2 into sine 2 into 2 pi is like 4 pi by t into t. Fine. So what you're able to see is that it has this, you can just write it as B1 sine omega, right? I'll just call it omega 1t, but and as you recall, omega 1 is the same as omega naught, right? Plus B2 sine omega 2t, and which happens to be just 2 omega 1t. Right? So which means that you are able to get these coefficients, and what by comparing with this what we had initially started with, which is hidden in the black box, and suppose that now you also are able to peek into the black box, then you can clearly see that both the signals are the same. Just that uh, just that B1 is equal to A1 and B2 is equal to A2, right? And of course, omega 1 is the same and omega 2 is equal to 2 omega 1. So that is where you are able to say decompose the signal and get the Fourier transforms. I mean, get the Fourier series. Now we move a step forward. Now we write something called as a Fourier. Let's draw it in terms of what we call as the, uh, in various ways we can call it, but let's sometimes it's also referred to as power spectral density and many other such terms, right? So in a simple sense, let's just call it amplitude versus frequency. So it's like omega and amplitude. So for a Fourier series, what happens is, in this case, all that we had is omega 1 was the fundamental frequency. And so there are two components. So this one is like omega 1, and this is 2 omega 1. So what happens is in this graph, this will be some value. Of course, usually it so happens that in most of the natural signals, it's always the lowest frequency, which is of the highest amplitude. And then this is our A2. So this is like A2 and this is A1. So when you're for this signal, A2 is Y2 is equal to A1 sine omega 1t plus A2 sine. Of course, it's the same. So omega 2t. So this is what will be what can be called as, so to speak, the Fourier, say the amplitude frequency diagram of that signal. Right. So without going into much into like the okay, without going much more deeper into Fourier transform. So this is what you call as the amplitude, or this is eventually the result uh, of any, after say doing the Fourier analysis of any signal. This is what eventually you would want to know. Fine. Now, for any irregular signal, irregular signal is signal which are not clearly uh, periodic signal, right? Any irregular signal, we cannot use Fourier series analysis. It does not make sense, right? So what we in such signals, so for any irregular signal x of t, what we do is we use something called as Fourier transform, right? So it's like then in that case, x omega will be equal to, there are many ways of writing this. Usually some books prefer it to write as t is equal to minus infinity. So t is equal to minus infinity, 2 is equal to plus infinity, and then x of t and e to the power minus I omega t and integrated over this. So this is what we call as the analysis step. And then what you have is the synthesis step. So we can just, so this is called as the Fourier transform. Now let me introduce this term called Fourier transform. And then x of t will be 1 by 2 pi and integrated over again minus infinity to infinity, but this is this time for omega, and we'll write it as x of omega e to the power I omega t and then d omega. Right? Okay, so this part is done, and this step is called synthesis step. Like we want to synthesize the signal back from the say the analyzed part or the decomposed part. So this is what we call as the inverse Fourier transform. Fine. Now, in such signals, what happens is once you do Fourier transform, then our goal is to plot x of omega, and it so happens that many a time x of omega, unless you don't have a periodic signal, right? So x of omega can be it can be complex, right? However, we would want to say just plot the amplitude and the and of course omega is going to be real because that's how we have put in our form expression itself, right? So omega is the like it now in this case here, and omega was discrete. It can only take the values of omega 1, omega 2, 3 omega 1, and like that. In this case, omega can take any value from minus infinity to infinity. However, it so happens that anything below less than 0 does not make sense. So what happens is, in general, the signal is always symmetric about omega is equal to 0 axis. So we would only plot in the first quadrant where omega has a non-negative value. So it will have some value, some graph like this. So in this case, we had just a set of vertical bars. Here it will be more as a continuous function. However, when you say when you want to do Fourier transform of this signal or this signal here, like this signal, if you want to take the Fourier transform of the signal using this generic approach, the one we are talking about, then here you would just get a set of points. So it will be the same way. It will be like this. So you'll have omega 1 and this will be 2 omega 1. In that case, the Fourier transform will be a discrete form, in discrete form, right? So my way of saying is the whole goal of this was that Fourier transform gives us the frequency content of a signal, gives the frequency content of any signal. However, there is something which is missing here. As in, let me give you an example. So say you have two signals, right? Say you have this signal here, which starts at t is equal to 0. And there is another signal which started from here. So t is equal to t1, right? So x1 and this is x2. Say we have added both the signals. Then you get some signal. Of course, I don't know how I'll be plotting it, but let's say I'm plotting it like this. Right, and all of it after t1 it just starts increasing. So say this happens to be our t1, and this is like t axis, and this is our this just xt of is just a sum of x1 plus x1t and x2t. Then if you do Fourier transform and say this one was omega 1 and this one was omega 2, this the frequency of the signal, right? So you do Fourier transform. And all that Fourier transform gives is that it will give that, okay, there are two signal components at this and this. And this is like x of omega and omega axis. So this will be omega 1, omega 2. Just that. It does not tell, it gives the frequencies of the component signals. But there is one thing that it does not tell us. And I know it may be obvious. It does not tell about time when the component signal emerged or appeared, or when because there are multiple component signal, right? So when a component signal appears in a given signal. So it does not give us any information about T1. So like gives component, but no information about T1, about T1. And this, I'm telling you, the thing is because say if the frequency, if the signal was say stayed for some time and then it ended at T2, T is equal to T2. And after adding, of course, just assume that this x of t is just the sum of both, and this just keeps on going. It also does not tell you about x2, about t2. So it's like you neither know when a signal component appeared and when it disappeared. And that is one of the, or I could say, I mean, which is relevant to this course that we are talking about, is that this is the biggest advantage of a Fourier transform, that it does not tell us the appearance of or disappearance of a component signal. So there is where that's what I wanted to talk about. Why wavelet transform? That is the story, right? Right. So it was like the issue is that it only gives us it does not tell us anything about time. So say you have say one frequency here and say some frequencies here. So here you can even translate it to this part. It doesn't tell us anything, like time is not known in the frequency and during the Fourier transform. Like it does not tell us anything about the appearance or disappearance of the signal. So this is like it's invariant with time. It's invariant. And this time means actual signal time, right? Just to clarify, it is signal time. So it's invariant. You can put this bar anywhere, it doesn't make it only because Fourier transform only tells about the frequency. However, there is this thing about wavelet analysis is that this is what we call as the temporal localization. So for example, if a frequency appeared here, say some frequency appeared here, and it lasted for this long, and one frequency appeared here and lasted till this time. Or for the signal that we are talking about, say just just in the previous slide. So it is as if, so frequency omega 1, again I'm again using interchangeably. Frequency usually denotes, I mean, you'll find that in practice we mean angular frequency. We also refer to angular frequency as just frequency, right? This is like omega 1. Let's write it here. And so because what we know about this component signal with frequency omega 1 is that it stays forever. It started at 0 and stays forever. However, for omega 2, it seemed that it started at some omega at some time, and this was the frequency was omega 2, and it ended here. T is equal to T2. That's it. As simple as that. And this is only possible in, of course, we can have other transform, but let's say it is possible in, that would be better framing of the sentence. It is possible in Fourier wavelet transform. So this thing, what we call as the temporal localization. So just like Fourier transform, it gives us information about frequencies. So let me not, just to make these things clear, right? Let's put it at the same level. So it only tells us the points. It only gives us points. This point and this point. And you can even keep it anywhere because it does not tell us anything about time. So this one was omega 1, omega 2, and this is omega 1. So it's and this getting to know the frequency content of a signal is what we call as the frequency localization. Frequency localization is common to both. However, in only wavelet transform, what you have is the temporal localization, that you can get where and when a signal appears and when the same signal disappears. So that is the main disadvantage. I mean, sorry, the main advantage of wavelet transform or frequency transform. Right? And so this was the difference that we were to talk about. And what you will do is, let's go back and try to understand some of the fundamentals of a signal, right? Again, some more things which were discussed in the during the lecture is what we had called about. We had talked about the scaling. I mean, the properties of a wavelet. But at first, the property of a signal. Let's start with that. Right. So some properties, or maybe these are some quantities, I would call it rather. It's not just a, so like some uh, quantities related to, I'll just call it some quantities. So first of all, we talked about what is given a signal x of t. Then energy of a signal, energy is equal to the entirety of the signal squared dt, right? So this is the energy of signal. And here is where I would want to point something, that Fourier or even any transform for analyzing any signal requires that usually we see energy as referred to as E as a function of x, right? E of x, such that E of x is less than infinity. So what we call as that energy must be bounded. So any signal must have finite energy. That is the required. I mean, a very much required before we analyze a signal. If the signal is not bounded, then we cannot decompose it, because it does not make sense, because you would never find any such kernel. Usually, okay, I have introduced one more word here. So this is called as kernel, or to be more, we can in this for this in this context we can call it so the kernel of transformation, or kernel of the transform. And that's the reason I said that you can always construct your own transform. You can just name whatever you want and define your own constraint, own transform. So in that sense, the only thing that changes is kernel. See this. So this is the kernel for our Fourier transform. And for Laplace transform, as you may recall, Laplace transform has a kernel which is e to the power minus st, where s is a complex number. Right? So likewise, in even in wavelet transform, you will have different kernel. So what a generic, again, just digressing from the topic, any these are concept, this they form what are called the integral transforms. So a general integral transform is something, say x of some quantity is equal to minus infinity to infinity, the signal xt, and this will equal as I of some quantity dt. So this is what is the integral kernel, right? And this will vary depending on the transform that you want. And of course, you can always construct your own transform. So that was one such property related to that. And the other properties are about something called as the L2 norm or LP norm. And some people who have watched the videos will already be knowing of this. So I'll just be revising this. So LP norm of any signal f is x is minus infinity to infinity. Take the absolute value of or the p norm of x of the signal, right? And then take and of course integrate it over this infinity over the interval minus infinity to infinity and take the pth root of this. And p should be greater than 0 and of course, P must be real. So P is an element of R. And some sort of uh, and I mean some sort of other different special types of norms were also talked about, right? And we also talked about some sort of the space of functions and all. Fine, that is true. But today we would move in some other direction as well, like we would be actually diving into wavelets. So let's know some of the fundamental uh, mathematical requirements. So I'll just call it uh, some preliminaries, right? Some mathematical preliminaries. So first of all, what we start with basis. And of course, this basis is something which is very much widely used in linear algebra. So basis is a linearly independent spanning set, linearly independent spanning set. Of course, there will be, I would be introducing some terminology and then there will be some other terminology which opens up, which comes up, right? So all that I mean is that basis is something which will be linearly independent and it must span the entire space. Of course, there's too much words. So the idea is, as an example, let me give you something about polynomial space. You may have heard of polynomial. What is a polynomial? So polynomial, say of x is just say a naught plus a1x plus a2x squared plus a3x cubed dot 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 a n x to the power n, and it just goes. So here, where a naught, a1, a2 till an, right? Till an, or of course till infinity, they are all an element of R. Like they are all real numbers, right? So what happens is any polynomial will always be defined for, say, this is what we call as, this is called as a polynomial space, right? So any polynomial, any arbitrary polynomial, say q of x, can always be defined by the linear combination of, so this is also as if in the first thing, sorry, even the first term here can be written as a naught into x to the power naught, right? So even this you can write as a naught into x, no x to the power 0, which is just 1. So I'll just call it a naught into 1, right? So the ideally you have 1x, x squared, x cubed, xn, and this goes on. So which means that any polynomial can be expressed as a linear combination. So by multiplying, and of course, say what do you mean by linear combination? So linear combination is what we have already known. Like this is a linear combination. So what we are doing is a naught into 1 plus a1 into x plus a2 into x squared plus a3 into x3, like that. So these a1, a2, a naught, a1, a2, a3, and likewise even an, x, and right, even an here, they are all what we call as the multiplicative factors. Let me write it properly. They are all multiplicative factors. Right. So what we mean by here is that you can express any polynomial just by taking a linear combination of all these points and of all these of all the terms in this basis. So this is like a basis. This is a basis for polynomial space. I'll just call it polynomial. This is a basis for any polynomial. Now, however, when you want, say for example, you want to express 4x squared. So 4x squared can be written as 0 into 1 plus 0 into x plus 4 into x squared plus 0 into x cubed dot plus 0 into x and this goes. So which means that say you will also be able able to express 4x square in using this basis. All that was that a naught had to be 0 is 0, a1 right. So it so happens that to write 0 in this basis, right? So when you want to write 0 in this basis, say you want to express 0 in this basis, then what happens is the only way to get 0 using this basis is when you have 0 into 1 plus 0 into x plus 0 into x squared. Likewise for every case, which means that a naught is equal to 0, a1 is equal to 0, and all a1s are all the a1s are 0. So which means that 0 can only be written in this way. So this is what we call as the linearly independent. And I just want to tell, I mean, to let you to explain it intuitively rather than giving all those long expressions about what do we mean by linearly independent. So linearly independent means to write 0 in any basis, the only possible way is by multiplying by being able to multiply all the terms using all the terms with zeros. That's the only way, which means that all the multiplicative factors must be 0. So then that set is linearly independent. And spanning means that this is called spanning of the set. So this is a spanning. But this is called the span of the set. Spanning set means using the one set, one basis, right? Or using one set, which by multiplying with multiplicative factors and adding them up can give you any member of the space. So in this case, to get any polynomial, we can just multiply all the elements of this set by some multiplicative factors and add them up, and voila, you have your base. You have this, the member of the polynomial space. So that is one thing, one preliminary, that one of the concepts that we want to introduce. The second concept is about what we call as the compact support. Now, compact support is, before, of course, telling you about compact support, we need to talk about what is called as global support. Then the meaning becomes obvious from the context. Global support. Now, what do you mean by global support? So take an example of a sine wave. Just goes and on. There is no end to it. Even this side, even minus infinity, it goes till forever. Plus infinity also, it goes till forever. And this is what we have, sine omega t, where of course omega is not equal to 0. Right? This is how a sine omega t looks like. That it always has non-zero values. I mean, it has non-zero values. That is a better way to say it. It has non-zero values throughout the time axis. Right? So it seems that sine omega is not 0, right? Throughout the time axis. And of course, it is 0, but certain points, right? So sine omega 2 is of course 0, but more it has non-zero values. I think this people may just take this very strictly, right? So I'll just write it in a different way. So sine omega t has non-zero values, I would say. Non-zero values throughout the time axis, or time line, or what we call as the time axis, of course. Time axis is nothing but just the real line, or the real number line, right? So which means that this is what we call as, which means that sine omega t has global support. So once you get to know the meaning of, I mean, global support, then of course it's very easy, so to speak, comparatively to understand what is a compact support. So compact support means that the signal has support only over a limited segment of the time axis. So say for example, this signal, right? So this is till here it is 0. So I'll just call it signal yt. So yt is 0, and here also yt is 0. So yt, and let me call it minus t1, and this to be t1, right? So which means that, and this is not equal to 0. So which means that yt is equal to, is not equal to 0 for all t which belongs to the set minus t1 comma t1, and it's always 0 for otherwise. Right? So which means that, and this of course this t1 is again to be more to be very precise, t1 is finite. Right? So which means that yt has compact support. Right? Because it has non-zero value only over a limited segment of the real axis, or which also happens to be the time axis, right? So like these are some of the important terms. And now we'll just talk a bit about wavelet, the definition of a wavelet, the proper definition of a wavelet. The definition of a wavelet goes as a wavelet is a wave function with a compact support. Right? And the reason it is called a wave, now it is called a wave due to its oscillatory nature. And minus let, which is this hyphen let, sorry, hyphen let suffix is used because of the finite domain where it is different from 0. And this is what is, that is the property, or what that is the definition of a compact support. Right? And then there is a fundamental concept, is what we call as, there is something called as a basic wavelet. So you have something called as a basic wavelet, or even sometimes we refer to as parent wavelet. Right? So parent wavelet it, right? So you have this psi of x, and even this psi of x has certain properties, and we will keep it for the next session, because of course this has not yet been covered in quite detail, but let's just give a very overview of some of the properties of a mother wavelet. So some of the properties of mother wavelet is, first of all, zero mean, which means that integral of minus infinity to infinity of psi, of course I'll call it psi of t because we are dealing with a function of time, psi of t dt is equal to 0. That's the first thing. And second thing is unit variance. So unit variance means minus infinity to infinity. Of course, what we mean by, the way we define variance is some signal or some quantity or some random variable in probabilistic language, some random variable minus its mean or expectation. In this case, mean is 0, whole squared and integrated. So this will be minus infinity to infinity psi squared t dt. This must be equal to 1. So these are some very fundamental properties of a mother wavelet, and what we call as the children wavelet. And children wavelet, we referred in plural. They define the wavelet basis. Now they are obtained by scaling, and like say they are obtained by scaling, which means that, and dilating is the word that was used even in the lecture, and translating the mother wavelet. And the way we refer to the children wavelet is AB, right? Again, as a function of t is equal to 1 by root over a psi t minus b divided by a. And here a is greater than 0, right? And what we can see here is b is called as the translation factor. Right? So we call b as the translation parameter and a as the dilatation or dilatation parameter. So and then you have two subscripts in psi, and they are a comma b, right? Which means that they denote what we have as the signal, so to speak. They denote the parameters, or they identify the signal, or they identify the wavelet, right? So this is uh, the definition of a wavelet, right? And of course, we will be talking further about more properties in the next class. Before that, let's do some solved examples. And of course, this is more like just reviewing what we have, right? So what we have been trying to do. Say a question which is some, of course, assignment live problems, like problems not exactly from the assignment, but which will help us in solving some of the assignment problems. So say one problem is, say, given a function ft is equal to integral of e to the power minus, say, just minus t, or maybe you can call it minus of absolute t, right? And it, so let it be, let's just call this the signal that we want to determine the, we have this, sorry, this is the given signal. And we are asked to determine the Fourier transform. Right? So the idea is, of course, we had talked about Fourier transform, is that, so we usually refer to as the the signal as in lowercase letter, and its Fourier transform as its uppercase version. So it will be capital F and a function of omega. And this is going to be equal to, of course, minus infinity to infinity. And that we have is f of t e to the power I omega t and dt. Fine. Now, when we put this signal in this uh, expression here, when we just input the signal, so what we have is e to the power minus t e to the power minus I omega t. Right. So this is what our signal happens to be. Fine. Okay. So what we can do is, So we can divide the signal in two components. Since this we have this absolute value on t, so we can write it as say minus infinity to 0, and you have minus the absolute value of t e to the power minus I omega t dt, plus this is just the basic thing that we may have learned during our school years, which is like you can just break us integral into two forms by just changing the limits, right? Then we have e to the power minus absolute value of t e to the power minus I omega t dt. Now, absolute value of t. So the way we define absolute t is this is equal to t if t is greater than 0, and this is equal to minus t if t is less than 0. Because you want the absolute, I mean, if t is negative, then minus into minus is just plus, right? Because the absolute value of t has always has to be positive, right? Except at 0, then this is becomes from here, and then all we have is it becomes minus into minus, so it becomes plus t is the power minus I omega t dt, and here it is just e to the power minus t, right? And then uh, so here what we have is e to the power minus I omega t dt. So it will be like just keep it as e1 minus I omega t dt plus 0 infinity e to the power. So it will be 0 here, and say minus t plus I omega, sorry, 1 plus I omega t. And the way you know the integral of e to the power x, right? So e to the power ax dx is nothing but e to the power ax by a, and over the limit. So in this case, it will be e to the power 1 minus I omega t divided by 1 minus I omega from 0 to, so from minus infinity to infinity. 1 of infinity to 0. And likewise, here it will be e to the power minus 1 plus I omega t divided by minus 1 plus I omega, and then from 0 to infinity. And the rest you know what to do now, right? All that is some algebraic manipulations. So this minus comes here. So all you have is put e to the first 0, so it will be 1. At first it will be 1 by 1 plus, let me slightly to get some room here. Sorry. Just to get some room. So this will be 1 by 1 minus I omega, and putting um, t is equal to 0, so it becomes e to the power 0, that is 1 minus, and then you have t is equal to minus infinity, and you know that e to the power minus infinity is just 0, right? So it will be 0. And of course, there will be some restriction, but let's take it to be 0. Then minus, and in this part we have is 1 by 1 plus I omega. So again, e to the power minus infinity is what happens is just 0 minus again e to the power, so it becomes 1 by it just becomes 1. So eventually we are left with is 1 by 1 minus I omega plus 1 by 1 plus I omega. And as you recall, it becomes a, so since we had a real signal, so even our Fourier transform will be real. So it becomes 1 plus I omega plus 1 minus I omega. So I omega cancels out, divided by 1 minus I square omega square. So it is like 1 plus omega. So it means that f of omega is equal to 2 by, right? It is, so it's 2 by 1 plus omega squared. So you see that even the Fourier transform is real. And if you plot it, then of course you'll be getting at omega is equal to 0, the value will be 2. and otherwise at omega is to infinity, of course, this is going to be infinity. So the way it will be something like approaching zero at very low, very large value of omega. So this is the graph. Right. Okay, so this was one such problem, and I believe there are many such problems in the assignment, which of course I cannot solve it since the assignment is yet not is due. But anyway, we can always discuss if you would like some hints, then we can always discuss in the next class. Since okay, so I hope things have been well understood. So do you, any of you have any doubts or something like that?
No, sir. No.
Okay. So yeah, so the thing is, yeah, this was an introductory class, but we since the way we have defined is we want to cover more material than what would be covered in the course. So of course we'll be sometimes be faster as well compared to the official lecture videos. And yeah, so I think with this we can call it a day if that is what we want today. And let's meet again in next Friday at the same time.
Thank you,
Right?
sir.
Okay, sir. Thank you.
Okay. Thanks.
Yes,
Thanks
sir.
everyone. Yeah.
Thank you, sir.
Okay. Yeah.
Thank you, sir.